Great. This is all about sequences and series. We're starting chapter 12. And so this is, unless you've had this class before, this may be the first time that you've seen this. And that's great. A sequence is, I have some blanks on your handout to fill out. It says a sequence is a function, what's the word that goes right there, that computes an ordered list. That is what it is. The domain of a sequence is different from a regular function. So the domain of a sequence is the natural numbers. So let me talk about the domain real quick. It is the set of natural numbers. Now, it might have been a while since you have discussed set theory. So the set of natural numbers is denoted by the capital letter N, and it also has another name called the counting numbers. Because when you're going to start to count up the number of objects that you have, you start with the number 1. And it's the same thing with the set of natural numbers. This is the set. This little braces means the set of all. And so 1, 2, 3, 4, and so on. So the natural numbers are the positive whole numbers. And that is what the domain of a sequence is. You only put in positive whole numbers. Okay, so the notation, let's talk about the notation next. The notation for a sequence, normally we have a function called f of x, maybe is equal to 2x plus 3, let's say. Well, in our situation, if it's a sequence, instead of using f of x, we use a sub n, replaces this. And so n replaces the independent variable x, the domain. And the reason they use an n is because that reminds us that the input is natural numbers. And so the rule would be 2n plus 3. So instead of writing our function like this, we write it like this. A sub n is equal to 2n plus 3. And we understand that this type of function, the input to it is only the natural numbers. Okay, so that's the notation that we'll be using here. Now, the range of a sequence is what a sub n is. So the f of x is, again, this would be y, right? So in function notation, x is the input or the domain, y is the output or the range. In sequence notation, n, little n, 1, 2, 3, 4, is the input, and a sub n is the range. So a sub n, so a sub 1, a sub 2, a sub 3, and so on. These are the range numbers, and these are referred to as the terms of the sequence. So the range is the terms of the sequence. Okay, so that's the basic notation things we need to look at. Let me see, what did I want to say here? Now let's look at if we were to graph one. So I have these grids on here. So I picked a few different ones for us to look at. Let's look at the sequence a sub n is equal to n plus 3. For the first one, let's look at a sub n is equal to n plus 3. Let's do it for this one. And then the next one I want to look at will be a sub n. The rule will be a sub n is equal to 1 over n. Okay, and then the next one I want to look at will be a sub n is equal to 1 over n plus 2. Okay, we're going to take these one at a time. So the input is the natural numbers. So if we were to put in n is 1, when n is 1, down here, ready? When n is 1, then y is or a sub n, a sub 1. So so right here, n is 1, then let me do this in purple. When n is 1, a sub n, or a sub 1 is equal to 1 plus 3 or 4. So when n is 1, a sub 1 is 4. So 1, 1, 2, 3, 4 is the first place we'll put a point on this graph. Okay, so this is 4. All right, so what about the second term when a is 2? Okay, when a is 2, then n becomes 2. 2 plus 3 is 5. So when we're at 2, then we're up here at 5. 5. And when we're at 3, when you put in 3, 3 plus 3 is 6, we're up here at 6. 3, we're at 6. And then we're at 4, 4 plus 3 is 7. And so you can see how this is going to take place. So this looks very linear in nature. This particular sequence is linear in nature. They are not all linear in nature, but this one is. And so the thing I want you to take note of is that this is the output, the graphs of a sequence, the graph of a sequence is discontinuous. Okay? What I mean is this space in between is not part of the sequence. It skips dot to dot, basically. And so since those dots are not joined in between, it's discontinuous function. So that is important. The graph of the sequence is discontinuous. And that will be the same for all of these. Okay, let's go ahead and let's plot a sub n is 1 over n. Okay, so for the blue graph, if we come up here and we say, okay, well, let's see. What's going to happen here when a is 1, when n is 1, and when n is 2, and when n is 3, and when n is 4? What happens here? Okay, for the blue graph. Okay, a sub 1 would be 1 over 1, which is 1. Okay. A sub 2 would be 1 over 2, which is 1/2. A sub 3 would be 1 over 3, 1 over 4. Okay, let's look at this. Okay, when n is 1, right here, this is our blue graph. Okay. The output is 1. When n is 2, the output is, 1/2, halfway up. When n is 3, it's only a third of the way up. And when n is 4, it's only the fourth of the way up. And we can see it's going to get smaller and smaller and smaller as we go down the line. Okay. We also, this is also discontinuous. Every graph of a sequence is going to be a discontinuous graph. Okay. Let's look at this one, the red one. A sub n is 1 over n plus 2. All right, let's put some input in here. A sub 1 would be 1 over 1, which is 1 plus 2. So that's 3. A sub 2 would be 1 over 2 plus 2, that's 2.5. A sub 3 would be 1 over 3 plus 2, that's 2.33. A sub 4 would be 1 over 4 plus 2, that's 2.25. What's going to happen here? Okay, this is the red graph, 1, 2, 3, 4, 5. Okay, so when A is 1, the output, the first term is 3. 1, 2, 3. We're up here. All right. When n is 2, a sub 2 is 2.5 right there. When a is 3, when n is 3, a sub 3 is 2.33 right there. Maybe it's right there. A sub 4 is 2.25. Okay. So we can see as the terms increase, as n gets bigger and bigger, it gets closer and closer to the line. It's getting closer and closer to. I think I need to look at how I drew this. Oh, I went way too. Let me just get these a little bit better. This is supposed to be at 1, it's supposed to be up here at 3. At 2, it's supposed to be at 2.5. At 3, it's supposed to be at 2.33. At 4, it's supposed to be at 2.25. Okay, this is better. It's supposed to be there. So, again, this graph is discontinuous. But what can we say about a couple of graphs that we can't say about the other? One of these graphs is called divergent, meaning as n gets bigger and bigger and bigger, a sub n does not get close to a certain number. So that would be the purple graph. As n gets bigger and bigger and bigger and bigger, A sub n gets bigger and bigger and bigger and bigger. You can see what's happening here, and it's not converging. It's not getting close to a single number. In fact, it's approaching infinity. So that would be called a divergent series or sequence. Okay. However, look at the blue graph. As n gets larger and larger and larger, a sub n, the terms get closer and closer and closer to a certain number, and in this case, they're approaching 0 as we keep getting bigger and bigger and bigger. So since as n increases, as n gets very large, n gets close to a value, which is 0 in this case. So this is a convergent. It converges to 0. All right. So what was happening with the purple? What made this divergent? The fact that as n got large, a sub n did not approach a single value. That's what made that divergent. Okay, look at the red graph. As n gets very large, our graph is getting close to, it's approaching the number 2. So as n gets very large, a sub n gets close to the number 2. It converges to 2. This is also a convergent sequence. So that's the difference in divergent and convergent. Okay, so now the next thing I think I have is something called a recursive sequence. Okay. I keep saying series. What a series is the sum of a sequence. So sometimes I accidentally toggle those words. Sequence is simply the list with commas, this after this after this. A series is when you add up those numbers. So we're going to be talking about that in a minute. A recursive sequence is a sequence in which the future terms are defined by the previous terms. Are defined, I should say, not by, but using. Using the previous terms. Okay, so there are many infinite amount of recursive series. We could make them up all day long. But there's a very, very famous one, and I've listed some of the numbers on your sheet. It's a very famous recursive series, and the numbers go 1, 2, 3, 5, 8, 13, 21, 34, and so on. And maybe you can pick up on the pattern, what's happening here. But this famous set of numbers that goes on and on and on forever is called the Fibonacci sequence. This is in fact why I have the picture that I do when you go into Canvas and you look at our course. There's a picture of a nautilus shell. This shell pattern follows the Fibonacci sequence. In fact, there are many things in nature that follow the Fibonacci sequence. And so I would like you to watch the short video, it's very short, on the Fibonacci sequence and answer the question. I would like you to list 2 places in nature where it occurs. But you can't use the nautilus shell because I just gave you that. So list a couple of other ones. There's plenty to pick from. And so watch that video, and then when you come back, we're going to finish up this worksheet.